A woodpecker strikes a tree trunk, again and again. 12 times per second, the beak connects with solid wood. Each impact lands with precision. Fragments scatter. The sound is sharp, repetitive, controlled. The deceleration on each strike exceeds 1,000 times the force of gravity. A human experiencing even a fraction of this, just once, would suffer concussion, permanent injury, possibly even death. This bird does it 12,000 times a day. There is no helmet, no padding, no external protection of any kind, just bone, tissue, and a brain sitting millimetres from the point of impact. This should cause brain damage and hemorrhaging, swelling, the accumulation of trauma that eventually ends function. Every known principle of impact biology says this behaviour cannot be sustained. Yet the bird keeps on going. It isn't dazed, it isn't slowing down. It's feeding, excavating, communicating, performing the behaviour that defines its existence. Something here does not add up. This isn't a story about a bird with a built-in helmet. It isn't a tale of nature's perfect engineering, or even a single miraculous adaptation that solves everything at once. That version gets repeated often. It's simpler, it's satisfying, it's also incomplete. What allows a woodpecker to function is not one feature, but a system, built from constraints, trade-offs, and compromises that don't always align. To understand how this bird survives, we need to stop looking for a clever trick and start looking at the problem itself. What forces are involved, what would fail first, and what a solution would actually require? Because the answer isn't padding, it isn't cushioning. In fact, absorbing impact may be the very last thing that this bird needs. The real question is more specific and more interesting. How do you build a head that can deliver thousands of high-speed collisions and still function the next day? Woodpeckers are found across much of the world. More than 200 species occupy forests, woodlands, savannas, and even deserts. They range from birds no larger than a sparrow to species approaching the size of a crow. But an extremely high percentage of them share one defining behaviour. They use their heads as tools. Pecking serves three main purposes here. The first is feeding. Woodpeckers excavate bark and wood to reach insects, larvae, and sap hidden beneath the surface. Some species probe, others chisel, and some drill methodically through solid timber. The second is construction. Most woodpeckers carve out their own nest cavities, a process that can take weeks of sustained effort, hollowing chambers in dead or living wood. The third is communication. Many species drum on resonant surfaces to establish territory or attract mates. This drumming is distinct from feeding. Faster, more rhythmic, and often performed on the loudest surface available. So not all pecks are equal. A light tap to locate a hollow section in the wood is not the same as a full force strike against hardwood. A territorial drum is rapid but shallow. A feeding excavation can be slower yet far more forceful. The intensity varies, the frequency varies, but across all of it, the head remains the point of contact. The skull, the beak, the brain, all millimetres from the repeated impact. The physics of collision make it dangerous for almost any creature with a centralised nervous system. So how does the head survive repeated impacts? The obvious assumption is that a woodpecker must absorb the shock. Padding, cushioning, some structure that softens the blow before it reaches the brain. This assumption is wrong. High-speed imaging and biomechanical models show that the woodpecker's skull does not deform on impact. It does not compress. It does not flex inward to absorb energy. And if it did, the bird would actually fail at its own task, because a woodpecker is trying to drive force into the wood, not dissipate it. Any energy absorbed by the skull is energy that never reaches the tree. A soft, shock-absorbing head would be inefficient. Each strike would do less work. What the bird needs instead is stiffness. It needs a head that transmits force cleanly and efficiently, more like a hammer than a helmet. This reframes the problem. So the question is no longer how the woodpecker cushions impact. It is how it survives the full transmission of impact over and over again. To see why that should be lethal, we need to briefly look at physics. When a woodpecker strikes, the beak stops almost instantly, but the brain does not. The brain, suspended in fluid, continues moving forward and presses against the inner wall of the skull and then rebounds. This movement and the impact up against the inner wall of the skull is the basic mechanism behind concussion. In humans, this kind of motion tears blood vessels, stretches axons and triggers inflammation. Even a single high-speed impact can cause lasting injury, and repeated impacts accumulate serious damage. A woodpecker strikes at a speed around 6 to 7 meters per second, stopping in well under a millisecond and therefore experiencing peak decelerations that can exceed 1,200 times gravity. This is far beyond the roughly 100 G associated with concussion in humans, or the 9 G that can cause blackouts in fighter pilots. And it does it thousands of times a day. This is not just mild stress, it is exposure to forces that should destroy the brain tissue, and yet the bird continues. Now, the explanation, as we've seen, does not lie in softness. It lies in precision, geometry, and scale. The woodpecker's survival is not the result of a single adaptation. It comes from several features working together, each addressing part of the problem. So back to stiffness. The skull is dense and rigid, reinforced where forces are high, and the beak is not a separate tool attached to the head. It is continuous with the skull, forming a single unit built for force transfer. When the beak strikes wood, energy moves straight through the skull as a pulse. This matters because stiffness transmits force efficiently. As we've seen, a skull that flexes or absorbs impact would waste energy and increase internal stress. Heat, vibration and deformation would damage tissue and would also reduce effectiveness. A woodpecker doesn't want to absorb impact. It needs to pass it forward into the tree. Stiffness is not a weakness here, it's essential. The second part is brain size. A woodpecker's brain is absolutely small, weighing only a few grams. This dramatically reduces injury risk. Brain damage scales with mass. When the skull stops, a heavier brain carries more momentum and therefore exerts greater pressure when it presses up against the cranial wall. A smaller brain experiences the same deceleration, but with far less inertia. It moves less, deforms less, and generates significantly lower internal forces. There is simply less tissue to displace. This is not a protective feature evolved for pecking. It is a constraint of the bird's features that works in its favour. Small brains, easier to stop. Third is alignment. Woodpeckers strike in an almost perfectly straight line. High-speed footage shows minimal rotation, no glancing blows, and little lateral movement. Beak, skull, and neck align along a single axis of impact. This matters because rotational forces are far more damaging to brain tissue than linear ones. In humans, twisting motion inside the skull is the primary cause of diffuse injury. Woodpeckers largely avoid this. The alignment is behavioural as well as structural. The tail braces against the tree. The feet grip with 2 toes forward and 2 toes back. The body forms a solid, stable tripod, locking the head into position before each strike. Now, the fourth thing to consider is muscular control. The head is not simply thrown at the tree. Neck muscles accelerate the strike and then stabilise the head immediately after impact. The same system that drives the motion also stops and controls it. This limits recoil. The head does not bounce off the tree. The brain does not slosh back and forward side to side. Motion is controlled, timed, and repeatable. There is also evidence that woodpeckers close their eyes just before impact, preventing displacement of the eyeball under force. The timing is precise. The whole system is beautifully synchronized. So no single feature explains survival. Stiffness alone would still allow rotation. A small brain without alignment would still shear and bounce around. Straight strikes without control would still recoil. What works is the combination. Stiffness transmits force, small brain size limits momentum, alignment prevents rotation, muscle control limits rebound. Each solves a problem, the others cannot. Woodpeckers possess an anatomical feature that immediately draws attention: the hyoid. In most animals, it is a small structure that supports the tongue. In woodpeckers, it is elongated into a ribbon-like bone that begins at the tongue, loops around the entire skull and anchors near the face, forming what looks like an internal harness inside the head. The idea is intuitive. A bony structure wrapping around the skull kind of resembles reinforcement, a strap, a brace, or a built-in safety system. Early studies proposed that the hyoid might absorb shock, dampen vibration, helping protect the brain during impact. That explanation spread very quickly. It's neat, visually pleasing, and extremely satisfying overall. But more recent biomechanical research very much challenges it. When researchers modelled the forces involved, they found that the hyoid is actually poorly positioned to absorb meaningful impact energy. It is thin, loosely attached, and sits away from the main axis of force. During the pecking, the tongue is typically retracted, which further slackens the hyoid, rather than placing it under any tension. That does not mean that the hyoid does nothing. Some studies suggest it may help stabilise the skull laterally, limiting small side-to-side motion. Others propose it may dampen residual vibration after impact. If these effects exist, they are minor, and the hyoid is certainly not a crash cage. It is not the core solution to repeated head impacts. Its primary role is feeding. Woodpecker tongues are unusually long, extending far beyond the beak to extract insects from deep tunnels. The wraparound hyoid allows the tongue to be stored compactly and deployed with speed and precision, and that function is well established. What remains uncertain is then whether the same structure contributes meaningfully to protection, or whether its apparent suitability has simply made it an attractive explanation. What makes the hyoid worth discussing here is not what it does, but what we assume it does. When people look for explanations, they look for visible structures. A bone that wraps around the skull invites metaphor. It looks like human-esque protection, so it becomes the answer. But biology rarely works that way. The survival of the woodpecker, as we've seen, is not explained by a single, dramatic, easy to categorise feature, but by a system. One where effectiveness is distributed, constrained, and actually counterintuitive. And now there is one more part of that system that matters far more than it appears. For decades, the assumption was simple. Woodpeckers do not appear impaired, therefore they must have solved the problem of brain injury. In 2018, the assumption was complicated. Researchers examined preserved brain tissues from woodpeckers and compared it with tissue from non-pecking birds of similar size. They were looking for the tau protein. This is a molecule associated with brain injury in humans. Tau is not inherently harmful. In healthy neurons, it helps stabilize internal structures. But when brain cells are damaged by repeated stress or trauma, tau can accumulate in abnormal patterns. In humans, this accumulation is strongly associated with chronic, traumatic encephalopathy. This is effectively significant, notable, and chronic brain swelling. The study found elevated tau in the woodpecker samples. This was unexpected. It raised a difficult question. Do woodpeckers sustain brain damage from their pecking, from their natural behaviour? The answer is unclear. The presence of tau does not prove injury. We cannot assess cognition, memory or behavioural decline in wild woodpeckers. The birds examined were already dead. We know what their brains contained, but not what the effects were. Tau may also function differently across species. What signals pathology in humans may be tolerated, managed or repurposed in birds. It is possible that what looks like damage represents a stable state rather than degeneration. The study itself was limited. The sample size was small, and the follow-up research has been sparse. The finding has not been overturned, but it has not been robustly replicated either. What it did, though, was change perspective. Woodpeckers were once treated as proof that nature had solved high-impact trauma. Their skulls were studied as models for perfect protection. After Tau's findings, the certainty weakened somewhat. The bird may not be fully protected. It may simply be functioning within damage. It may be operating close to a boundary rather than beyond it. That does not mean the system has failed. It means the picture is incomplete. This pattern is not unique to woodpeckers. Cheetahs sprint at speeds that risk overheating and joint failure. They do not run safely. They run close to their limits, fast enough to catch prey, often enough to survive. Deep diving mammals descend to pressures that should collapse lungs and flood tissues with nitrogen. They manage, but not without cost. Beaked whales strand with signs of decompression injury. Elephant seals surface carrying oxygen depths that would incapacitate a human. Bar-headed geese cross the Himalayas at altitudes where oxygen is thin enough to kill. Their physiology allows it, but just barely. None of these animals have completely solved their problem. They operate within it and within its limitations. And the woodpecker fits this pattern. Its skull is stiff because stiffness is required. Its brain is small, its strikes aligned, its muscles precise, and still tau accumulates. Still, the margin of error may be very, very narrow. What looks like a miracle is often just a very tight tolerance. Across the animal kingdom, the same structure repeats. An animal does something that appears impossible. We search for a single adaptation that explains it. And then when we look closer, we find not a solution, but a compromise or a negotiation. Evolution does not design for perfection, it selects for survival. An organism does not need to be optimal, it needs to function long enough to reproduce. A woodpecker does not need an injury-proof skull. It needs a skull that holds together through the years that matter. If damage accumulates slowly, if failure comes late, selection pressure is weak. The system is tested not against an entire lifespan, but against survival and therefore reproduction. And by that measure, it 100% works. So, there we see. The system works, but potentially it does not work with much room to spare. Every strike a woodpecker makes depends on alignment. The angle must be correct. The neck must be braced. The muscles must fire in sequence. A deviation, a glancing blow, a mistimed contraction, and the forces change. Geometry that normally protects the brain can quickly become damaging. This is not a system built for error. It is built for repetition under very, very narrow conditions. Young woodpeckers do not hatch knowing how to peck. They learn. Early strikes are clumsy and inefficient. Precision is acquired gradually through practice. Even in adults, the margin remains thin. A branch that gives way, a surface harder than expected, a parasite that weakens coordination. Any of these can shift the balance. We tend to see animals as finished products, optimized and secure. But reliability is not the same as safety. A system can function consistently while operating close to failure. The woodpecker does not appear to have much of a buffer, but it has just enough of what it needs to survive for long enough to carry out its task. A woodpecker strikes a tree trunk 12 times per second, thousands of times a day. Forces that would destroy most brains pass through its skull and into the wood. It survives not because it's immune to damage, but because it has found a way to operate within damage. Stiffness instead of softness, precision instead of padding, a small brain, a straight path, a system that controls what it cannot eliminate. The old story was that the woodpeckers evolved the perfect shock absorber. The reality is far less tidy. They evolved a system that is adequate, one that holds together long enough under specific conditions for the bird to live and reproduce. That is what evolution builds. Not perfection, not invincibility, just enough to keep going and fulfill a task. Woodpeckers did not evolve to be indestructible. They evolved to survive a task that makes damage likely. Not normal, just workable. These films do take time to make, and I want to push the research and the visuals further with each one. If you do enjoy this kind of work, and you'd like to see more of it, your support genuinely helps, so please do consider liking and subscribing. Thank you for watching, and I'll see you next time, exploring life at the edge of what's workable.